Thanks everyone for sticking with us through some slight technical difficulties. We're right back on track, ready for our next presenter. But firstly, thanks to Arjun for a comprehensive technical presentation on the mechanics of induced seismicity. That flows very nicely into our next speaker, who's Dr. Peter Hennings. He's a senior research scientist at the University of Texas Bureau of Economic Geology, where he's principal investigator for the Center for Injection and Seismicity Research and a lecturer in the Department of Geological Sciences, following a 25-year career in the petroleum industry. His expertise includes induced seismicity, structural geology, seismic structural analysis, and reservoir geomechanics. Dr. Hennings will be sharing with us some lessons from induced seismicity in Texas, and this is a really important and useful context because in 2022, the number of magnitude 3 earthquakes in Texas, nearly all of which were induced, was on par with that of California. So this provides a really rich laboratory in which to study the mechanics of induced seismicity. Peter, over to you.
Thank you so much, Katie, and good afternoon, everybody. It's a great pleasure to be here. My thanks to Interspace, Katie and Taylor for organizing the session, and the production team. I'll note that Katie is also a co-principal investigator in our Center for Injection and Seismicity Research at the University of Texas. So I'll discuss some of the things we've learned or things that have been amplified to us through the lens of induced seismicity in Texas over the last decade or so. And I'll have these observations and these recommendations show up again at the end of the talk. And so I'm just going to move into some of the more technical materials first, and then we'll come back to these at the end. Induced seismicity in Texas and southeast New Mexico has historically occurred in 6 provinces, and I'll focus on the areas in the colored boxes, including the blue box, which is the Fort Worth Basin, the green box, which is the Eagle Ford Shale play area, and Arjun had an example from there in the last talk, and the Delaware and Midland subbasins of the greater Permian Basin of West Texas. In the chart on the bottom right, you can see that the rate of magnitude 3+ earthquakes per month for these areas, shown in the graph in the same colors, gives us the earthquake history per area, and the black line shows the overall rate for all of Texas. The dashed black line shows the 12-month moving average. The rate began to increase in about 2010, especially in the Fort Worth Basin in blue. The Eagle Ford began to contribute next, and then the Delaware and Midland basins began to dominate the rate, mainly in the Delaware Basin in the last few years. However, we can see now that the overall rate is significantly reduced, which is thanks to the collective action of the Texas Petroleum Regulator, operators and operator groups, and researchers. So in the talk, I'm going to touch on some of the examples from the colored boxes, beginning first with the Fort Worth Basin. From 2005 through 2019, the injection of over 2 billion barrels of produced wastewater from hydraulic fracturing operations into the strata directly overlying geologic basement resulted in the rupture of deep faults and the occurrence of 10 earthquake sequences that you can see in the map. And these sequences remain spatially and temporally distinct, as studied by a very comprehensive seismologic program run by Southern Methodist University, and all the dots in the graph show individual earthquakes from their catalog. The injection maxed out at over 20 million barrels per month, with earthquakes up to magnitude 4.0, many in close proximity to injection centers. Comprehensive mechanistic analysis shows that the pore pressure increase from injection, as experienced by independently mapped faults causing the seismogenic rupture, ranged from about 1/3 of a megapascal increase, or 40 to 50 psi, in areas near injection centers like the A and V examples in the plot. We also have the I case, which represents a much smaller pore pressure change, maybe just under 10 psi, that occurred at great distances from the injection centers, but in close proximity to population centers. So we have proximal inducement at higher pressures, 40, 50 psi, and distal inducement at lower pressures, presumably channeled along faults that may stretch a distance of up to 50 kilometers, connecting areas of injection from faults that experienced the ruptures. The greater Permian Basin now of West Texas and Southeast New Mexico has, in general, 4 induced earthquake provinces. 3 in the Delaware Basin, which is on the left-hand side of the slide, and 1 in the Midland Basin with earthquake magnitudes of up to 5.4. Using this cross-section, which has data liberally projected into it, the earthquakes in the Midland Basin and the Northern Delaware Basin, that's this area here and this area here that I've circled, follow the same story as for the Fort Worth Basin, being induced from deep injection as hosted along basement-rooted faults. Earthquakes in the Southern Delaware Basin, in this area here, produce rupture on strata-bound faults in the sedimentary section with magnitudes as high as only a 4.3. New fault mapping and hazard assessment by Lily Horn shows the extent of native rupture sensitivity of the larger fault systems that pervade the entire Permian Basin region. The warmer colors in this map are the fault segments that are more sensitive to induced rupture from stress change. Focusing now on the Midland Basin for a few slides, we see the expected nature of the larger scale basement-rooted seismogenic faults as structurally complex in the more zoomed in map, complex and highly segmented, where high quality geophysical data is used for mapping and fault characterization. In the Midland Basin, the maximum rate of monthly deep injection of 70 million barrels per month dwarfs that of the Midland Basin, which only had a few million barrels per month, and has induced the earthquake history shown by the black dots on the screen. That injection into the deep strata has reactivated approximately 600 kilometers of this regional network of faults that strike to both the northwest and the southwest within a corridor that follows well-established tectonic fabrics in basement, which we'll come to in the last graphic slide. New comprehensive geologic characterization and pore pressure modeling of the deep injection strata indicates that the pore pressure increases in the Midland Basin associated with these recent fault ruptures range from about 100 to over 500 psi of pore pressure increase. And there's also a strong fault parallel directional diffusivity bias along the faults, but I won't go into that here. This graphic shows our model of the evolution of pore pressure increase from a deep injection from 2015 in the upper left through 2022 in the bottom of the slide, and then the earthquake sequences that developed over that time, as shown in the bottom slide. This is basically the same graphic, but now in detail. I'm showing colored samples along the faults. And those colors represent the degree to which this pore pressure change over the last 7 or 8 years has gone to an elevated condition above the predicted rupture stability of the faults. In some areas of the basin today, the pore pressure increase from injection is hundreds of psi higher than the native fault stability. And what we see today is now over 1,000 kilometers of fault trace length is at supercritical conditions using our mechanically uncoupled pore pressure approach. The induced seismicity in the northern Delaware Basin is very similar to the Fort Worth Basin, with inducement both proximally to pore pressure change. There's a pore pressure map on the right that's from Katy and some of those earthquakes that are induced locally. And then there's also distal inducement in this system as well. Down here in Culbertson County of Texas, these earthquakes being induced from stress change from injection much farther to the north. This zone in Culbertson County, at times itself more active than all of the earthquakes in California, is really quite a paradox and must represent a very sensitive fault zone within the underlying geologic basement in the Delaware Basin region. The induced seismicity system in the southern Delaware Basin in this region here is also complex, with shallow injection, heterogeneous compaction of production reservoirs, and mainly hydraulic fracturing, all contributing to the induced seismicity history. But the rate of earthquakes most closely tracks the rate of hydraulic fracturing operations in this part of the Delaware Basin. So the Delaware Basin is indeed a microcosm of induced seismicity and geomechanical sensitivity, with deep and shallow fault rupture shown, a surface expression showing strong co-seismic signals, and a history now of ground surface uplift from injection and subsidence from shale production, which is a testament to the geomechanical sensitivity of the subsurface of the Delaware Basin, with an application to understanding induced seismicity and general geomechanical sensitivity. Lastly, earthquakes across the Eagle Ford Shale Play area are known to be induced from hydraulic fracturing, and most have occurred on faults that are quite easy to rupture with the magnitude of pore pressure increase that accompanies fracturing. And we find that over a third of the fault trace length, as now mapped in the Eagle Ford region, can be made to rupture with pore pressure changes of less than 300 psi, which is far greater than pore pressure change experienced with hydraulic fracturing. And most of the earthquakes are occurring within 1 kilometer of an independently mapped fault. So Texas is quite the laboratory for studying injection-induced seismicity, with a wide variety of geologic settings and operational influences contributing within the petroleum realm. And it's quite straightforward to conclude that the study of fault systems that have and have not ruptured by stressing from injection of all forms provides vital clues to understanding injection-induced seismicity in general. So I'll conclude by amplifying observations that we really already know, that faults lay dormant for hundreds of millions of years can be easily seismogenically reactivated with injection from hydraulic fracturing and large-scale injection, either nearby or distally. Faults are complex conduits for fluid and pressure transmission. Hydraulic fracturing can cause fault rupture at relatively large distances, and we're seeing examples of up to 15 kilometers between areas of hydraulic fracturing and resultant fault ruptures. Large-scale injection can cause rupture at especially large distances, and we have examples of up to 50 kilometers in that case. Stratabound or overburdened faults can change their slip behavior from one mode to another, and in the southern Delaware Basin, from being seismogenic early in life to being aseismically slipping later. So finally then, some just very broad recommendations. From the perspective of the geologist, it's all about understanding the faults and the hydraulic system extent and the connectivity. Site characterization using the highest resolution and modern data is essential. And we recommend to not be fooled into thinking that fault slip sensitivity analysis should be or can be relied upon without detailed local and recent earthquake data. And with that, Katie, I am finished. Thank you.